Welcome to the wonderful world of physics. This is the beginning of the unit on electromagnetism in Physics 104B. We start with Chapter 20 on electric charge, force, and field. And this is Section 21, electric charge. In ancient times, there was known a substance called amber, and the Greek word for it was electron, and there you can see it written out in the Greek language. It was called electron. It was this hardened residue from trees, and they noticed that it had some weird properties, that two charged pieces of amber, and by charged, I mean if it was rubbed with fur or wool or something, sometimes they would, when hanging next to each other, they would repel each other. And in more modern times, it was found that plastic rods would do this as well. And in more modern times, glass rods will repel each other. And this gets into experiments that Benjamin Franklin was doing. And then it was discovered that if you have a piece of amber that is rubbed with fur or wool or some cloth, and a piece of glass, and by the way, you can see on the screen I say amber/plastic. So plastic is more in modern times. It has the same properties as amber in this regard. But if you have those and you rub them, they will attract each other. So the two ambers would repel each other, the two glass rods would repel each other, but an amber and a piece of glass would attract each other. And Benjamin Franklin was considering why this was happening, and he attributed it to an electric fluid that was held in all substances. And he said that the difference, or whether they would attract or repel, had to do with whether there was a deficiency or an abundance of this electric fluid. And what he figured was that the amber and the glass, that the amber had a deficiency in this electric fluid, and the glass had an abundance of it when you rubbed them with cloth or wool. And so when they came near to each other, they would attract each other as if the abundance in the glass wanted to jump over to the deficiency of the fluid in the amber. And sometimes they would see a little spark jump, and they figured that was the electric fluid. Now, if you take two glass rods, both of them having an abundance of the fluid, then it was figured that because they both have an abundance, they don't want to be near each other, so they repel each other. Now, Benjamin Franklin, first of all, he was wrong about this idea of electric fluid, but he realized he had a 50-50 chance guessing which one, the glass or the amber, has the abundance and which one has the deficiency, and he didn't know, so he just picked one, and the glass has the abundance, the amber has the deficiency, and it would have worked the other way around, but that's what he went with. And so what we see is that like charges repel, meaning these two materials, if they're like each other, meaning if both are negative, both are deficient in the electric fluid, they will repel each other. Opposite charges attract. So if one is deficient and the other is abundant, they will attract each other. Now, you can see in the drawing, I've put positives for the abundance and negatives for the deficiency, so these became known as positive and negative charge. Well, later on, with better experimentation, learning more about atoms and the parts of the atoms, it was realized that what was going on was there wasn't an electric fluid, but rather there were protons and electrons. Protons have positive charges and electrons have negative charges. So the amber, which Benjamin Franklin thought was deficient in electric fluid, what's really going on is when you rub it with cloth or wool, or you can even rub in your hair, it actually picks up an excess of electrons. So it's not deficient, it actually picks up electrons. The glass, when you rub it, and we say you charge it, it actually loses electrons. And so we call electrons a negative charge and protons a positive charge because of the designations that Benjamin Franklin originally gave those materials. It's a little awkward for the rest of the math that we'll do that the main particle of charge, having charge that we'll deal with, is actually negative charge. And if Benjamin Franklin had picked it the other way around in his 50-50 guessing and said that the amber has an abundance of electric fluid, we would be calling that positive and would make some of the math a little easier. But this is the convention that we have. Electrons are negative charge, we call them, and protons are positive charge. Now, atoms, which are made up of protons and electrons, they also have neutrons, but neutrons are neutral particles, and so we leave them out of the discussion. They're not relevant in this discussion. Atoms tend to be electrically neutral, meaning you add up all the positives of the protons and the negatives of electrons, and they tend to come out to zero, meaning equal numbers of protons and electrons, because protons and electrons have equal and opposite charges. Now, here's why generally in nature atoms tend to be electrically neutral. You look at the atom on the top, and this is one that has a charge of +1 because it has 3 protons in the middle and 2 electrons. Now, overall, this atom with the +1, +1, +1, and the -1, -1 has a charge of +1, and being positive, it is attractive to negative charges, so it is attractive to electrons. A nearby electron in the vicinity will be attracted to it and captured by it, and therefore it'll have a charge of 0 and it'll not be attractive to electrons. So in general, if an atom is charged, it'll tend to attract electrons and make it uncharged. Electricity is the source of many of the phenomena that we see in nature, in life, in the world, even if it's not something that we think explicitly as electrical. So when we think about electricity, we might think about lamps and lights and cell phones and computers, but electricity is pervasive in our muscles. It's what makes our muscles contract. It's what makes our heart beat. It's what makes much of our functioning of our bodies. Even when two objects press against each other, the normal force, that's actually electricity. So two objects pushing against each other, the outer electrons of one object and the outer electrons of the other object repel each other, and we get what macroscopically we observe as the normal force between them. But if you zoom in, here we have negatives and negatives. We also see lightning from clouds. So we have lightning is a charge difference between the ground and the clouds. And when there's a big enough charge difference, the electrons will leap from the one to the other. Now here's a picture of lightning striking a car. Many people know that you are safe if in a lightning storm you can seek shelter in a car. And a lot of people have a misconception why you're safe. A lot of people think it's something to do with the rubber tires that are insulating. But actually, you're safe because of the metal that the body of the car is made of. When the electrons come from the cloud down to the car, they want to make their way to the ground as quickly as possible. So they take the shortest, the quickest, the easiest path down to the ground. When it strikes a car, the first electron hits the metal of the car and it moves its way around and down to the ground. And the second electron hits and the third electron hits. And those electrons hitting very, very rapidly, millions and millions of them, they will actually spread themselves out across the body of the car evenly and go down to the ground. They will go right through the tires because the tires are not that thick with rubber. And so the tires do not insulate you from the ground, and that's actually a good thing. It allows the electrons to go straight down into the ground. What the electrons do not do is go through the interior of the car, and that's a good thing for our safety. So the electrons spread themselves out over the body of the car and go down to the ground. When we talk about electrical charge, the unit is the coulomb, named after Charles Coulomb. And a coulomb is equal to 6.25 times 10 to the 18th electron charges. Now, it was discovered through later experiments that there is actually a smallest possible charge that anything can be, and it's called the elementary charge, and we use the letter E for that. So the E does double duty. The E can stand for electron charge, or it can stand for elementary charge, but whatever you call that E, it is the smallest possible charge that anything can be. It is 1.602 times 10 to the negative 19 coulombs. And we don't have half E or 1/3 E existing by themselves. It's just this. Now that is the charge of a proton, positive 1.602 times 10 to the negative 19 coulombs, or we'll say it's positive E, and an electron is negative E. And of course, a neutron, being neutral, is 0. This has been a short section, but that's it, our introduction to electric charge. Have a great day.